Alright, so we're going to be going through my Sterlen of homework 7 for y'all. And so we'll have our const rs. So this s will have an asterisk. That asterisk means that instead of s being an actual character like maybe h, instead s is going to be an address. And hopefully what's at that address is going to be a character. And so we're going to be doing something called pointer arithmetic to solve this mystring.c file. And you guys have been doing pointer arithmetic this whole time in assembly. Every time we've given you like this label like array, we do like dot fill x4000. We've given you the base address of this array, and you guys, whether knowingly or not, we're doing pointer arithmetic to basically access the indices of these array, right? So if you wanted the third index, you guys did pointer arithmetic and did x4000 plus 3 to get x4003, and that would get you the address of the third index of the array. Does that make sense? And so C is going to be a very similar process here. We're given a const char pointer, and we can assume that this pointer is pointing to the base address of a string. And pointers don't have to be pointing to arrays, but we can assume it for this case. Pointers are very flexible. And C even has its own array data type. So you could make an array in C. But fundamentally, these arrays are fancy pointers. They have there's a little bit subtle differences that you might need to know of, the difference between arrays and pointers. But an array will actually eventually boil down to a pointer, well, to its base address. But for now, we'll get to those little nuances later. For now, we'll just treat this pointer as a base address. And so let's say we have a string called hello. Now remember that the end of every string will have a null terminator. Alright. That's something that we all agreed to do. And so if we can use pointer arithmetic to access the elements one by one until we find this null terminator, we can keep account of how far we have to travel to reach it. That's going to be our len. So C likes to represent anything representing the sizes or lengths of an object or a data structure in memory. They like to use the size t variable, or the size t type, not variable. And you can see it's just an alias for an unsigned long. And that's what type def means. It basically, you can give aliases to like pretty long types. So every time we're writing size t, like I equals 0, we're actually writing unsigned long equals 0. And it's better to do this, or unsigned long I equals 0. And for the purposes of this mysterlen function, we're going to be using size t to keep consistent with C's default behavior. And if you think about it, it makes a lot of sense, right? So in systems, like sizes can get really big, like it can be gigabytes, even terabytes sometimes. So we want a big number that can store it. The long part. And you can't really have a negative size of something, right? You can't have something that's negative 3 megabytes or something. So we'll make it unsigned. So we'll just be, instead of using like an int to store offset, which could work, we're going to be just trying to stay consistent and use size t. And so a general idea is that we're just going to have an I. We'll set it equal to 0. And this will be our offset. And we'll travel this pointer. We'll make a new pointer called s plus I. And yes, you can add a pointer and a value together. That's perfectly valid. And it'll start out in the first loop as pointing to h. And what we can do is we can do something called dereferencing. So we can start using our asterisks again. And when you define something, the asterisk kind of wraps it in a pointer. So it treats it as a pointer. But when after you define something, when you're evaluating things, that asterisk kind of goes in reverse and it starts unwrapping the pointers. So it basically travels the pointers instead. Just a distinction. This asterisk has different meanings based on when you're defining something or when you're like using something or evaluating something. But yes, we'll have this s plus I, and our first loop will start pointing to this h. And as long as it's not the null terminator, we're going to increment I by 1. And now s plus I, instead of pointing to h, it's going to be pointing to e. And it's not the null terminator, so we'll set I equals 2. Point it to L. On and on and on. And should be on the 5th loop, where s plus I will point to our null terminator. Or I guess a 6th loop technically. But once we find that, then our I is actually going to be the size of our string. And we can just simply return that. So that's the idea. So we'll start with size t I equals 0. We'll have something called while. And here's where I do our pointing arithmetic. We're going to do s plus I. And really, you have been doing this in assembly, whether you realize it or not. We've given you the base address, and you've always had to add this offset I to access specific elements. So now we added these two values together. It's still a pointer. So in order to travel that pointer, basically travel this arrow, we'll use our asterisk again. And that's going to basically take us to the destination of this pointer. And we'll have our actual value of our elements. The first loop, it should start out here. Okay. And then while this doesn't equal the null terminator, is this value, we're just going to be incrementing I. And eventually, once we find the null terminator, we'll just return our I. And so that's how we do pointer arithmetic in C. And this is really just, it helps a lot if you think of C as an easier way to do assembly. So we could easily have done this in assembly, but it's so much easier to do in C. Look how short the code is.